Hi there and welcome to this video for Senior Physics looking at atomic structure. In this video we're going to explain how the theories about the structure of the atom came about. Now basically the theories behind the structure of the atom were down to a number of key scientists, and so three of them are here on the right hand side of the page. We've got Ernest Rutherford at the top, we've got James Chadwick, and we've got Niels Bohr. And throughout this iTunes U course, we're going to sort of run through how these scientists actually came up with their theories that are accepted today. Now, basically, we know that the atom is made up of three main particles, and you can see those on the left-hand side. We've got protons, we've got neutrons, and electrons. But how are they arranged? Well, we start off with our protons. Our protons can be found in the center of the atom, and Ernest Rutherford found this using his gold leaf experiment, or evidence from the gold leaf experiment. As well as the protons, we've also got neutrons which exist. These were found by James Chadwick. Now, these protons and neutrons make up this dense positive area in the center of the atom, which we call the nucleus. And these particles are vibrating, and you can see them here vibrating. Sometimes they vibrate really happily, sometimes that vibration is really, really tough, and to the point that they can't hold it anymore, and they'll discharge particles, and we call that radioactive decay. So as well as the particles which we've got in the nucleus, we've also got electrons which are spinning around the outer shell. And they exist in orbitals or shell orbitals, and you can see here these are in a three-dimensional process. So it gives the appearance that the atom is actually in is a sphere. And what we'll find later on, especially when we look at our quantum mechanics, it's not quite so cut and dried that these electrons are definitely going to be in this specific area. So how does this help us? So we know that 99% of the mass of the atom is found in the nucleus, and the majority, that other 1%, is made up of the electrons on the outside. And we call the particles which are present in the nucleus nucleons. So the nucleons basically will be made up of the protons and the neutrons, which give the atom its mass. So what do we know about these particles? Well, we know a number of things. We know that protons, electrons and neutrons have a mass and a charge, and they all work together. Now we can see here in our table that on the top we've got our protons, then we're followed by our neutrons, and then we've got our electrons. Now you'll notice that the mass of the protons and the neutrons are identical. So we've got identical mass in the nucleus, but you'll notice that the electrons are tiny compared to the rest of the protons and the neutrons. As a result, we actually say that those electrons, their mass is negligible in relationship to the actual mass of the overall atom. So when we often say that electrons have a mass of 0, it's not true, but they're so small we can ignore them. Now, one thing which is also worth noting is that the charge of the protons and the electrons are identical. So you'll notice that they're both 1.6 times 10 to the negative 19 coulombs, but the proton is positive and the electron is negative. As a result, when they combine together, they basically produce a neutral atom. Now, what do we know, or how do we add this into our idea of how an element or an atom actually exists? Well, we know, you can see down here, that we've got a generic element, and we're going to give it the symbol X. Now we all know that basically the symbols of the elements are denoted with letters. We've got capital letters to start off with. If they have a second letter, it's always in a lowercase. That allows us to put elements together, and us to know whether the second letter is either an element, part of the first element, or a second element in a compound. So we always write capital letter for the first, and then a lowercase letter if it happens to have a second. What else do we know? Well, when we look on the periodic table, there are a set of numbers. Now there's a number at the top, which we call the atomic number. This is denoted in this case by Z, and then there's a number at the bottom, which is the atomic mass number. That's the mass of the nucleon. That's the mass of the particles which make up the atom. So let's have a look at a quick example. Here we've got carbon. We can see carbon has the symbol C, it's got an atomic number of 6, and it's got an atomic mass of 12. So what does this mean? Well, the atomic number at the top gives the element its position in the periodic table. As well as this, it tells us that there are 6 protons and 6 electrons. Now, if we go to the table at the top, we can see that the charge of the electrons and the protons are identical, except they're just one's positive and one's negative. So when we combine them together as they're equal numbers, the result is we've got a net charge of 0. So the atom is neutral. Down the bottom, when we look at the atomic mass, we've got an atomic mass of 12. That basically means that we've got 6 protons, which we've seen from the top. So to make up the other, to make it up to 12, we've got 6 neutrons at the bottom. Now, a way of determining the number of neutrons is by minusing the atomic number, the top number, from the bottom number, which is the atomic mass. So atomic mass minus atomic number will give us the number of neutrons. So that basically allows us to explain how elements exist in the periodic table and how we can read them. Now, elements don't always exist in one format. They often exist in what we call isotopes. But what is an isotope? Well, basically an isotope is an element of the same number of protons, but it has different numbers of neutrons, hence it's got a different mass. Now remember that the protons basically identify the type of element we've got, but the neutrons add to the mass. Now they've got different neutrons in their nucleus, so they're going to have different masses. Now you'll notice if we look at an example, say for chlorine here, chlorine has a position of 17 in the periodic table. It means it's got 17 protons and 17 electrons, and as a result it's got a neutral charge. But you'll notice down the bottom that its mass is 35.5. Now that doesn't make sense, because if you think about it, 35.5 means that somewhere along the lines we've either got half a proton or more directly half a neutron. Well, we can't have half a neutron, so where does that 0.5 come from? Well, the 0.5 basically is an average taken between the different isotopes of chlorine that exist on the planet. Now, chlorine can exist basically as a variety of different isotopes. It can exist with a mass of 35. In this case, it means that it's got 17 protons, and it's also going to have 13 neutrons. Or it can exist with 37. In this case, it's going to have 17 protons and 20 neutrons, and that adds up to 37. So what's happened is we've worked out the percentage of each of the different isotopes that we've got on the planet. And by taking an average of all the different percentages of the isotopes on the planet, they've come up with an average mass for chlorine of that 35.5. Now, some of these isotopes, because they've increased in mass, makes the actual nucleus very unstable, and because it's unstable they become radioactive, and often those radioactive particles can then break down, splitting the nucleus up, releasing energy and converting them into different types of elements. And that will be explored if you look at the nuclear radiation iTunes U course, which is created on the catalogue. So basically, when we look at isotopes, we look at the number of protons, the difference in the number of protons, and then we work out the average of those protons and neutrons and those masses to give an overall mass for the actual element for the periodic table. So let's have a look at an example. So here you can see we've got an example of magnesium, and it's found naturally in the Earth as 3 different types of isotopes. We've got magnesium 24 is 78.7% of the planet, magnesium 25 is 10.13% on the planet, and magnesium 26 is 11.17% on the planet. And what we want to do is to work out what the relative atomic mass of magnesium is. Now you can see on the right hand side here that on the periodic table magnesium has a position of 12 protons per 12 electrons, and it's got a relative atomic mass of 24. Now basically, where does that 24 come from? So what we've got, we can basically convert each of our percentages and our masses together to get an overall mass. Now you can see if I do 24, which is the mass of the magnesium 24, that's 78.87%. By converting it using the equation, I can get 18.8 mass atomic units. Same for the 25 and same for the 24. When I add all those together, the result is I come up with 24.322 units. Now that 24.32 is what we would find on the periodic table. In this case, it's just been rounded up to make an overall 24. So I hope that makes sense. I hope that explains how the structure of the atom is made up, with our protons, our neutrons, and our electrons, and then how you would identify them in the periodic table. This is a useful skill that you're going to need, especially when we're looking at radioactivity and understanding how the atom works. So I hope you found that useful. Do check out my website, aussiephysics.com, where you'll find lots of resources and more iTunes U courses which will link to the various concepts that we teach in physics. So thanks for watching, and I look forward to you joining me again. Bye for now.